Hello, my name is Vladimir Shatalov. I am a physicist, mathematician, Python developer, and data scientist. Welcome to my homepage.
Welcome to the deep dive. Today, we're really digging into the work of Volodymyr Shatalov. He's an R and Python developer specializing in that tricky space where math and data science meet.
Yeah, and our mission here isn't just to list off projects. We want to understand how these really complex academic ideas actually get turned into working solutions, stuff that solves actual business problems. We've got a fair bit of material here, projects ranging from logistics optimization, which sounds intense, to deep learning in finance, crypto markets even. The goal is to kind of distill the core methods and the tech involved.
Absolutely. What really jumps out is this coherent problem-solving approach. It seems grounded in applied mathematics, but the applications are incredibly diverse. We're seeing data science, financial math, basically using data analysis and forecasting to consult businesses, and the tools. We're talking Python, R, machine learning, neural networks, even trading algorithms. It's quite the toolkit.
Okay, sounds good. Let's maybe start with the logistics side. That seems like a really tangible place to begin. How complexity meets, well, the road. Good starting point. We really have to begin with what's often called the vehicle routing problem with pickup and delivery. VRPPD for short. It's highlighted here in a Jupyter Notebook project.
VRPPD. Right. For anyone listening who maybe hasn't battled that one, what's the actual, real world problem it's trying to solve?
Okay, so imagine you're running a delivery company, a big one. You've got a fleet of trucks. You need to figure out the best routes for all of them to pick stuff up and drop stuff off. But, and this is the hard part, you've got all these rules. Truck capacity, you can't overfill it. Pickups have to happen before their corresponding deliveries. And every single stop might have a specific time window you have to hit.
Ah, okay. So it's not just finding the shortest path. It's shortest path plus all these constraints sounds
It's difficult.
extremely. It's what's known in computer science as an NP hard problem. Basically, as you add more stops, the time it takes to find the absolute perfect optimal solution grows incredibly fast, like exponentially fast. So trying to just calculate every single possibility is out of the question for anything non-trivial. You'd be waiting forever. How did this project actually manage that complexity?
This is where you need specialized software. The source mentions using Google's OR Tools library. Now, this isn't just, a simple code library. It's a sophisticated optimization engine built for exactly these kinds of large-scale operational research problems. And crucially, to make sure the routes actually work in the real world, it integrated with the Google Maps Service API. That pulls in real road distances, travel times, makes it practical, not just theoretical math, all racked up in a Jupyter notebook.
All right, that makes sense. Tackling the micro detail of individual truck routes. But I also see notes on something related, but bigger picture. Optimal locations for logistics centers using postcode clustering. So this is about deciding where to even put the warehouses in the first place, right?
Exactly. It complements the routing problem perfectly. You can have the most efficient trucks in the world, but if your depots are in the wrong places relative to your customers, you're still wasting time and money. This project focused on using postcode data, specifically ZIP codes, for the contiguous U.S. coin to figure out the best spots for warehouses to maximize customer coverage.
And how does clustering help with that? What's the main factor it's optimizing for?
The key input, the thing they were really focused on, was the maximum delivery distance the business was okay with. In this case, it was set at 120 miles. So the algorithm's job was basically find the smallest number of central warehouse locations needed so that, say, 99% of customer demand is within that 120-mile radius of some center. It's a trade-off. Fewer centers mean lower infrastructure cost, but you still need good reach.
Right, balancing cost and service. And the result mentioned, it seems surprisingly low. 90 centers for the whole contiguous U.S.
It is a pretty striking number. The analysis showed that just 90 strategically placed ZIP code locations could cover 99% of demand within that 120-mile driving distance. That kind of finding is huge. It gives management a concrete number, a data-driven insight for deciding whether to build new centers, consolidate existing ones. It moves from gut feeling to actual optimization.
Okay, so that's a solid look at the logistics side. Optimization, geography, data analysis, really practical stuff. Now let's shift gears. This next area feels quite different, moving from physical routes to, well, predicting the future in volatile financial markets using AI.
Yeah, this is where we see the deep learning skills come in strongly. The example here is a Binance Cryptocurrency Market Analysis and Forecasting tool. Quite a mouthful.
Binance. Okay, so crypto trading.
Yeah.
The notes say it does real-time analysis. What does that actually involve? What makes it more than just like looking at a price chart?
It goes much deeper. It pulls data directly from the Binance API in real time, okay?
Yeah.
It visualizes the trade history, sure, but the key thing is it tracks the order book.
The order book. That's all the buy and sell orders waiting to be filled.
Exactly. It shows the immediate supply and demand pressure. By analyzing changes in the order book in real time, the tool tries to identify the underlying factors driving those tiny price movements, the oscillations. It's about understanding the why behind short-term volatility, not just the price itself.
Interesting. And for the forecasting part, the notes specifically mention an LSTM model, long short-term memory.
That's right, LSTM. It's a type of recurrent neural network, and it's particularly well suited for time series data like financial markets, especially volatile ones like crypto. Why LSTM? Well, simpler models often struggle when there are, long delays between important events in the data or lots of noise. LSTMs have these internal memory cells that help them remember patterns and information over longer periods. This makes them better at picking up on subtle, long-range dependencies that might influence future price moves.
So this project is a clear example of using TensorFlow. That's the framework mentioned for building and training these deep learning models.
Precisely. TensorFlow is one of the industry standards for this kind of work. The project involved building the LSTM, training it on historical data, and then, importantly, checking its performance using backtesting, seeing how well it would have predicted past movements, and then using it for future price prediction.
And this kind of financial modeling skill isn't just limited to crypto, is it? I see references to other financial math projects.
No, definitely not. The principles transfer. There's mention of a revenue versus risk estimator tool. That one calculates potential revenue based on cumulative daily returns, but also measures risk using rolling standard deviation. Pulls data from the Yahoo Finance API for regular stocks.
Okay, standard deviation for risk. Makes sense. And there's another one. Seemed really different. A lifetime well-being calculator using Australian life tables.
Yeah, that's a fascinating one. It simulates household financial health, projecting it out from retirement age, around 67. The really interesting part is incorporating mortality data from Australian life tables. So it's blending financial projection with actuarial science, modeling longevity.
Wow. Okay. So across these finance examples, the core skill is choosing the right mathematical or statistical approach, whether it's a complex LSTM or established actuarial methods, and then actually coding it up effectively.
Exactly, matching the tool to the task and having the programming skills to implement it.
Which brings us nicely to the next point. Just the sheer range of technical skills on display here. Moving from, say, VRPPD constraints to Binance market data. That requires a lot of different tools in the toolbox.
It really does. We've seen Python is clearly central, especially for the machine learning and data science parts, using things like TensorFlow and OR tools. But R programming also pops up quite a bit, often paired with something called RShiny.
RShiny, what's the advantage there? Why use that?
RShiny is fantastic for building interactive web applications directly from R code. Think dashboards, visualizations, ways for non-technical users to interact with complex statistical models. So projects like a Twitter sentiment analysis tool or a sales forecast tool, those are mentioned as using RShiny. It lets you quickly wrap a powerful R analysis in a user-friendly web interface. It shows focus not just on the analysis itself, but on making the results accessible.
Right, usability is key. Okay, just to kind of drive home the breath here, let's quickly mention a few other projects that seem to use totally different skill sets again.
Sure. There's an AI Telegram chatbot. This looks like applied natural language processing, NLP. It uses something called Llama Index and the OpenAI API. The specific angle here seems to be training it on custom documents, text files, PDFs, Word docs. So the chatbot can answer questions or analyze information based on a company's own internal knowledge, not just general web stuff.
Interesting. And then shifting gears again back towards more traditional stats, credit risk estimation.
Yeah, and this one highlights flexibility and platform choice. Instead of Python or R, the example shows credit risk models, like decision trees and logistic regression being built and compared using RapidMiner. RapidMiner is a visual data science platform. Using it suggests selecting the tool based on maybe client needs or industry standards for that specific task, like generating detailed confusion matrices to evaluate model performance.
Okay, platform flexibility. And one more, just because it sounds cool. The iterated prisoner's dilemma simulation.
Ah, yes, that one's really neat. It draws on evolutionary game theory, which has roots in biology and physics. It simulates how different strategies perform against each other over many rounds in the classic prisoner's dilemma game. Strategies like always cooperate or tit for tat. The simulation calculates the fitness of each strategy and watches how the population mix changes over time. It requires blending math, simulation modeling, and computation. Pretty advanced stuff.
So looking at the big picture, what we're seeing is someone who can take a really complex problem, often crossing disciplines like physics, finance, data science, and then apply a very specific, often high-level technological tool to get a concrete, measurable result.
That's the essence of it, I think. It's about that translation. Translating intricate problems into effective code that delivers quantifiable performance, whether that's cutting delivery costs or improving prediction accuracy.
We've definitely covered a lot of ground today, from optimizing physical routes with OR tools to using advanced LSTMs and TensorFlow for financial forecasting, all backed by this broad fluency in Python, R, and even platforms like RapidMiner.
And I think the key insight for you, listening, is how many of these big challenges, optimizing things, predicting things, often come back to similar fundamental mathematical ideas. But it's the mastery of these specialized tools and libraries, like TensorFlow, OR tools, Llama Index, that actually bridges the gap from theory to real-world impactful applications.
Absolutely. Which leaves us with a final thought, something for you to chew on. We've touched on some seriously complex projects, from VRPPD to sophisticated portfolio optimization. There was even a mention of something called the SIMDO method, Capital Impairment Maximal Diversification Optimizer, for stock risk management. Now, considering this huge variety and the fact that these fields change so fast, the source material indicates this developer works as a one-man team, explicitly stating no outsourcing. So the question is, what level of continuous adaptable learning, what kind of intense intellectual synthesis is actually needed for one person to stay genuinely expert across such a wide and rapidly evolving technical landscape? Something to think about.